The UML uses a set of symbols to graphically represent the various components and relationships within a system. It is mainly used to support object-oriented systems analysis and to develop object models. There are 5 main UML model types that are used during object-oriented analysis: use case, class, sequence, state transition, and activity. Each tackles the definition of the system from a different perspective. The system development process starts with the identification of events that trigger business processes called use cases and things that are problem domain classes involved in the business process. The question often arises as to which model to develop first. Since both aspects are closely related, they are usually defined together. The UML approach to object-oriented analysis requires several interrelated models to create a complete set of system specifications. Let's take a look at each of these model types. A use case represents the steps in a specific business function. An external entity, known as an actor, initiates a use case by requesting the system to perform a function. In UML, a use case is represented by an oval with a label that describes the action, while an actor is represented by a stick figure with a label that identifies the actor's role. A line between an actor and a use case is called an association. It links a particular actor to a use case. In this case, a passenger makes an airline reservation, a customer places an order, a bus dispatcher initiates a change pickup address activity. In software engineering and system engineering, use cases are a technique for capturing functional requirements of systems. Each use case provides one or more scenarios that convey how the system should interact with the users, called actors, to achieve a specific business goal or function. Use case actors may be end users or other systems. Use cases typically avoid technical jargon, preferring instead the language of the end user. Use cases are often co-authored by business analysts and end users. During the 1990s, use cases became one of the most common practices for capturing functional requirements. This is especially the case within the object-oriented community, where they originated, but their applicability is not restricted to object-oriented systems because, strictly speaking, use cases are not object-oriented in nature. Use cases can also interact with other use cases. When the outcome of one use case is incorporated by another use case, we say that the second case uses the first. This relationship is referred to as the includes relationship, sometimes as the uses relationship. UML indicates the relationship with an open arrow that points at the use case being used or included. To create use cases, you start by reviewing the information gathered during the requirements modeling phase. Your objective is to identify the actors and activities they initiate. For each use case, you develop a scenario or use case description which documents the description of the use case and a step-by-step list of tasks and actions required to successfully complete the activity. Other UML models can also be used to document the use case, including the activity diagram and the sequence diagram. This interrelated modeling is one of the greatest strengths of the unified modeling language. When you identify use cases, try to group all the related transactions into a single use case. A use case diagram is a graphical model that summarizes the information about the actors and use cases. To use use case analysis, a system developer looks at the system as a whole and tries to define all of its major uses. When creating a use case diagram, one of the first steps is to identify the system boundary. The system boundary shows what is included in the system. This boundary is the automation boundary and denotes the boundary between the environment where the actors reside and the internal components of the computer system. After you identify the system boundary, you place the use cases on the diagram and the actors and show the relationships. In this example, we have 3 actors that will interact with an auto service department. A typical service department might involve customers, service writers who prepare work orders, and mechanics who perform the work. The customer actor will request service that initiates the create work order activity. The service writer actor will write the work order. The create work order use case will use the update work schedule use case, which in turn notifies the mechanic actor. The create work order use case will also use the prepare invoice use case. The mechanic actor performs the work, uses the prepare invoice use case, and the service writer actor checks the prepare invoice use case. A class diagram represents a detailed view of a single use case, shows the classes that participate in that use case, and documents the relationship among the classes. A class diagram is a logical model that evolves into a physical model and finally becomes a functioning information system. When performing the analysis phase of your system design, the class diagram does not contain some details which will ultimately be required to build a working system. These details, which will be added during the design phase, include data type of attributes and visibility information, and method signature details such as parameters and return values. Each class appears as a rectangle with the class name at the top, followed by the class's attributes and methods. Lines show relationships between classes and have labels identifying the action that relates the two classes. Relationships between things apply in 2 directions. For example, a customer places an order describes the relationship in one direction, while an order is placed by a customer describes the relationship in the other direction. It is important to understand the relationship in both directions. That's why the UML notation allows 2 names, one from the perspective of the parent and one from the perspective of the child. It's also important to understand the nature of the relationship in terms of the number of associations between the classes. A customer may place multiple orders, but an order may be placed by only one customer. Cardinality refers to how many instances of one class relate to another, and is shown as a number phrase at each end of a relationship. In the unified modeling language, a class diagram is a type of static structure diagram that describes the structure of a system by showing the system's classes, their attributes, and the relationships between the classes. On this diagram, for a sales order use case, we have 6 classes defined: Sales Manager, Sales Office, Sales Rep, Customer, Order, and Items Ordered. Let's take a look at the relationships between the classes. The Sales Manager manages one and only one sales office. And a sales office is managed by one and only one sales manager. This is indicated by the cardinality 1 on both ends of the relationship. The sales manager manages 0 or many sales reps, and a sales rep is managed by one and only one sales manager. The 0 ... star notation is the UML mechanism for showing 0 or many. When 0 is included as part of the cardinality, it means the relationship is optional. The sales rep is assigned 0 or many customers, and a customer is assigned to one and only one sales rep. A customer places 0 or many orders, and an order is placed by only one customer. And finally, an order includes one or many items ordered, and items ordered is included by 0 or many orders. The 1 ... star notation indicates a mandatory relationship, meaning that if an instance of order class exists, then an instance of items ordered class must also exist. If you were to define inheritance or aggregation relationships, they would be drawn in much the same way, except they use a slightly different notation. Inheritance relationships are shown with an arrow pointing to the superclass, and aggregation relationships have a diamond on the owner end of the relationship. The third type of UML document used in the analysis phase is the sequence diagram. A sequence diagram is a dynamic model of a use case showing the interaction among classes during a specified time period. A sequence diagram graphically documents the use case by showing the classes, the messages, and the timing of the messages. A sequence diagram includes the following symbols. A class is represented by a rectangle with a name inside. The name can contain an object or instance name followed by the class name, separated by 2 colons. Classes that send or receive messages are shown at the top of the sequence diagram. The lifeline represents an object's life and existence during the time period of an interaction with other objects on the sequence diagram. A dashed vertical line is the symbol of a lifeline. An object symbol is drawn at the top of each lifeline. A message is a communication from one object to another, usually communicating an order to perform an action. A message is represented by a horizontal solid line from one lifeline of one object to the lifeline of another object. The time order in which these messages occurred is shown top to bottom. In this example, message 1 occurs before message 2. Each message can be labeled with a message name, conditions, and return arguments. Focus, or activation, shows the time period during which an object is performing an action. It represents both the duration of the action in time and the control relationship between the activation and its callers. An activation is shown as a tall, thin rectangle whose top is aligned with the initiation time and whose bottom is aligned with the completion time. Activation symbols are drawn on top of the object's lifeline. Objects that are deleted by a message or self-destruct during the time period of the interaction have a large X drawn at the bottom of their lifeline. A sequence diagram has 2 dimensions. The vertical dimension represents time, and the horizontal dimension represents different objects. Normally, time proceeds down the page. The dimensions can be reversed if you desire. Usually, only time sequences are important, but in real-time application, the time axis could be an actual metric. there is no significance to the horizontal ordering of the objects. Often, call arrows are arranged to proceed in one direction across the page, but is not always possible, and the ordering does not convey any information. In the example shown here, there are two classes. Each has its own lifeline as shown with a dashed vertical line. Class 1 sends a message to Class 2, and Class 2 responds with a message back to Class 1. After the message is sent to Class 1, Class 2 is destroyed, indicated by the X on the lifeline. The focus or activation period of each class is shown by the thin rectangle on the lifeline. The status condition for a real-world object is often referred to as the state of the object. The state transition model defines the dynamic changes that occur in the life history of an object. The understanding of the different states and the conditions that trigger the changes from state to state represent the programmatic modules that must be built to allow the application to perform in harmony with the real world. State transition modeling consists of defining each stable state of an object and then defining the triggers or events that cause the object to change to another state. For an example, an object customer order could be defined in states such as completed, backordered, partial, awaiting shipment, delivered, overdue, paid, paid in full, or partial payment. As the states are natural positions and the events or trigger actions on the objects, the transitions from one state to another represent the operations modules of a system. In addition, the attributes that define the state condition are established and can be used to develop the triggers and event processes. States are described as semi-permanent conditions because external events can interrupt a state and cause the object to go to a new state. An object remains in a state until some event causes it to move or transition to another state. A transition is the movement of an object from one state to another state. All possible states for an object must be documented on the state transition diagram and are represented by rectangles with the name of the state inside the rectangle. The small circle to the left is the initial state, or the point where the object first interacts with the system. Reading from left to right, the lines show direction and describe the action or event that causes a transition from one state to another. The circle at the right, with a hollow border, is the final state. In this example, a transition open account causes the state to change to new. A new action, make first deposit, causes the state to change to active existing. Then, assets are attached and the state is changed to frozen. If assets are released, the state is returned back to active. If a bank closes the account, the state changes to closed. Or if the customer closes the account, again, the state is changed to close. Then the state transition diagram ends. The activity diagram describes the sequencing of activities with support for both conditional and parallel behavior. An activity diagram is a special form of a state diagram in which the states represent the performance of actions and transitions that are triggered by the completion of the actions. The activity diagram can be attached to a class or to the implementation of an operation or a use case. The purpose of an activity diagram is to focus on flows driven by internal processing as opposed to external events. Usually, activity diagrams are constructed in situations where all or most of the events represents the completion of internally generated actions. The main components of an activity diagram include an activity, which is a state of doing something. It could be a task, such as receiving a payment, or the execution of a software routine, such as a method on a class. It is represented by a rectangle with rounded corners. A transition is represented by a solid line with a stick arrowhead connecting activities. Transitions are implicitly triggered by the completion of the activity preceding them. The transitions may include guard conditions and actions. It is labeled by a transition string of the form event followed by guard condition followed by action. All components of the transition string are optional. The start object designates the starting point of the activity diagram and is represented by a filled circle. The ending point of the activity diagram is represented by a filled circle inside a hollow circle. A synchronization bar is used to show parallel activities. It is represented by a black bar with one or more input transitions and one or more output transitions that are all taken in parallel. This means that the sequence of the output transactions are irrelevant. In order to show that all parallel activities need to be completed before the following activities, use a synchronization bar that has multiple incoming transactions and a single outgoing transaction. The outgoing transaction is taken only when all the incoming transactions are completed. And a decision is used when more than one activity can be performed based on a certain condition. There is a single incoming transition and several guarded outgoing transitions. The guards are mutually exclusive and only one of the outgoing transactions is allowed. A diamond denotes the decision symbol. The activity diagram shown here represents the actions and events involved in withdrawing cash from an ATM machine. At the start, the customer needs cash. The customer inserts an ATM card into the ATM. The card is accepted. The customer enters their PIN. The PIN is accepted. The customer requests cash. If sufficient funds are available, the ATM adjusts the account balance and then dispenses the cash. If sufficient funds are not available, the ATM notifies the customer and no cash is dispensed. Sequence diagrams, state transition diagrams, and activity diagrams are modeling tools that can help a system analyst understand how objects behave and interact with the system. Class diagrams, on the other hand, are static models which show the structure of the objects to be used in a computer system. Object modeling requires many types of diagrams to represent the proposed system. Creating these diagrams by hand is time-consuming and tedious, so system analysts rely on modeling tools to speed up the process and provide an overall framework for documenting the system components. In addition, a modeling tool ensures consistency because model elements that are created once can be used in different parts of the model without worry of duplication. Links between models can be maintained, such as linking a sequence diagram to a class diagram or an activity diagram to a use case. Visible Analyst provides the modeling tools necessary to create your object models. A tutorial on its use is provided in a separate session. When developing your object model, you should develop an object relationship diagram that provides an overview of the system. And you should organize your use cases and use case diagrams so they can be linked to the appropriate class, state transition, sequence, and activity diagrams. The models and documentation created during the analysis phase of the system development process will provide the foundation for the system design. When building your models, be as accurate as you can. It is much easier to repair a diagram now than to change the software later.